So hello, this is Mr. Fulmer here, and I was asked to. One of the things we didn't get too much this year was on rotational motion and torque, and actually angular momentum as well. So here are some slides that I put together that we'll go through. So when an object spins, it's said to undergo rotational motion. A couple different versions of that there in the animations. And one of the important parts of it is that you have an axis of rotation, a fixed point around which something turns perpendicular to the rotation itself. So if this was like the Earth, you have the axis of the Earth going through the North and South Pole with the Earth spinning around it, rotating around it. Toy tops have the axis of rotation going straight down from here. It has like the plunger and the tip. And then things like fans and propellers and that, you have the center, the middle, and everything, the wings or the fan blades going around that. Objects can actually rotate in multiple directions or dimensions at the same time. Our X, Y, and Z axes, which would give them multiple axes of rotation relative to each dimension. So for like an airplane one, you can have the axis of roll, the axis of yaw, and the axis of pitch. So the pitch would be like how you pitch up or down the wings. Axis of roll is you're physically rolling the plane, and yaw is kind of like actually doing like a turn. And if you've watched planes fly a lot, many times, basically the pilots are manipulating all three of those to get a smooth flight. Of course, for the physics behind that, that gets a little complicated with all the math. So we're gonna just keep it simple and talk mostly about one axis of rotation. And a big thing that we'll talk about in just a bit then too is center of mass. And because most objects aren't perfect circles, you do have lots of different ways to plot out the motion. For a person bending down, you have the kind of point of rotation, kind of in through here. If you're rotating with like the center of mass, just changing your shape can change where your center of mass is. That's actually what this picture is showing. Is if you're drawing like a free body diagram, here's like the center of mass and where the force of gravity is pulling down from the body. This one with the person kind of out further, the center of mass is out further as well. So this would be like where like a natural rotation point would be. So radius from the axis of rotation, general units are in meters. So a nice little circle diagram here. However far away from your axis of rotation, from that center point, the pivot point, out to wherever you're examining, that's your radius. S is arc length. So if you're driving in a circle, this would actually be the distance that you travel. So it's part of the circumference. And then you have theta, which is the angle through rotation occurs, measured in radians. Oftentimes also in degrees, but we convert back and forth for those. So as you're swinging out, you have, like on this circle, if you have two objects, one on like the circumference here and maybe one at like half R, both of them would travel the same angle, but they would have a different distance. So further out, the longer the radius is, the more the S length would be, the arc length would be. So That actually becomes really important depending on your situation. So a little bit of history in that. Um, um, Physics related to history in that. For like World War II, uh, you'd have these big formations of bombers that would go over Germany in that. And one of the missions that was quite dangerous, they actually didn't get the target cleared, like the weather didn't clear underneath the target in time, so they had to basically do a big circle and circle back to it. Except the airplane formation was so big that you would have the center of the rotation, but the formation of planes would have to stay in formation for it. So the planes closer to the middle, they would have less far to go, so they would slow down a bit, as slow as they can, and the planes on the outside of the formation would have more distance to travel, so they actually had to speed up so that all the planes would like travel in this line. So that's like one of those practical things that you can start thinking of when you're thinking of rotation. It's like, wait, what am I actually measuring? Am I measuring how much of the circle I've traveled, or am I looking at the distance I'm traveling? So a little bit of radians, depending on what you remember for geometry, perhaps. 360 degrees is 2 pi radians. So half a circle is 1 pi radian. So the complete circle is 2 pi. 1 radian is approximately 57.3 degrees. And 1 degree is 0.0175 532 radians. So using your stoichiometry, you can convert back and forth with those. So, kind of going beyond the arc length, what we really kind of start looking at is the angular displacement. How much of the circle, how many radians of that circle do you move? So for this one, if you're lifting the block up, it looks like almost 90 degrees. Your angular displacement is at like 90 degrees. And one way you can calculate that, or go back and forth between it, is looking at your change in arc length over the radius. You'll see a lot of stuff in rotation. If you divide by the radius, you end up being able to convert from like linear stuff to angular stuff. So for this one, the change in your angular displacement is your change in arc length over that distance from the axis of rotation. And this is really the power of gears, kind of a preview here. Your little gear, as this turns, like if this does 90 degrees, it only has so much of the arc length difference. So then this gear goes the same arc length. So if this one turned like 90 degrees, maybe this one only turned 45 degrees. And that's one of the power of gears, is you can basically manipulate the advantages there. We consider angular displacement positive when it's counterclockwise, negative when it's clockwise. Angular speed is the rate at which a body rotates about the axis. Radians per second. Looks like that got hidden. There it is. There we go. So linear speed, we talked about like the distance over time. Angular speed, it's the change in angle over time. So the theta over time is your omega, that little fancy W. So if you're doing like the angular speed of the Earth, you could say that it's 2 pi over 24 hours, and you can convert that to whatever units you'd like. So you can convert the 24 hours into seconds, or if you're really picky, the 23 hours and 56 minutes. I forget the exact time. But it describes the rate of rotation measured in radians per second, or sometimes we do it revolutions per time. Like the Earth, you'd have one revolution every 24 hours, or one rotation per day. And just like when we really talk about velocity in that, the omega here, the angular speed, is really the average of your change in the angle over that change in time. And we have displacement, we have velocity, and now we have angular acceleration, the rate of change of angular speed. We have radians over seconds squared. It is done by the Greek letter alpha. It looks like the fancy A, or sometimes people draw it more like the fish. And all points on a rotating rigid object have the same angular acceleration and the same angular speed as all other points on the object. If this was not true, the object would have to be changing its shape as it rotated. So one of the classic examples is using like a record, a music record. It doesn't matter where on the record you put the needle. Going underneath it is always going to be that angular speed being constant. It might travel more or less distance, depending on how far out from the axis of rotation it is, but the angular speed itself will be the same there. Or if it's accelerating, the acceleration, all points along it, that alpha will be the same. And what's kind of cool about all this is the same equations that we use for translational motion, the linear motion, apply here. So distance is speed times time. Hey, look at that! Your angular displacement is equal to your omega times t. V is equal to v naught plus at. Omega is equal to omega naught plus alpha t. And so on, so on. That we have our other two favorite equations there. Not that we had to memorize much this year, but what's really cool there is if you know the one form of the equations, you know the other. So I like the phrasing here. They're like twins in a different reality, linear and angular quantities. You also have something of the tangential velocity. And that's you can actually find by taking your angular velocity times whatever radius that you want to know how fast the circle is spinning. Basically. It's also if you have like a rolling object, if you know the radius, you know the angular speed, you can get the translational, the linear velocity for it. So tangential speed is the linear speed of an object directed along the tangent of this object's circular path. And if the object were to shoot straight off from the spin, it would go in that straight line at that tangential speed. So if you're spinning something around over your head over and over, and you let go, wherever it is on the circle, it's going to go off in a tangent then. and at whatever speed that you were spinning it at. Tangential acceleration is the instantaneous linear acceleration of an object directly along the tangent of the object's circular path. So it's a measure of the acceleration of an object over a short interval in the linear direction as the object is speeding up or slowing down, moving in a circle. Really, some of the math there, it ends up just basically being borrowed from calculus. Centripetal acceleration is the acceleration directed towards the center of a circular path. So if you have this one, you have like a spinning object. The ball, if it has no inward force, like towards the pause here, the ball's going to just basically fly off on a tangent. For this one over here, you have some sort of surface that provides a force pointing towards the center. So centripetal acceleration, centripetal force is always pointing towards the center. The kind of translation, the meaning with it is center seeking. So as an object spins around the fixed axis, there's a force that a lot of people call a force. I like the quotes, air quotes on this, that pushes ball outward and tries to keep it moving out in a straight line. But there's a real force that pulls the object continually back towards the center of rotation. So you have what people call the centrifugal force, and then we have the centripetal force. Actually, I think that might be a spell. I don't know. I'll have to double check that later with the D. On that outward force that we feel, that's basically inertia. Inertia, we want to keep moving in whatever direction we are going in. So if you're going in a circle, you're always wanting to go off on a tangent. So it's the more away from that center of rotation, the more inertia tries to keep the object moving outward. So if you're again, like on a carousel would be a good example. If you're kind of close to the center, you're moving a little bit slower. You feel less of that inertia than if you're on the outside of a larger carousel. You would feel more of that inertia trying to kind of push you outward. But, whoops. For the example of this ride, you're going to have the force that's actually making you rotate is that centripetal force. And that's basically the normal force on the outside of the ride pushing you towards the center. Like these kids are, inertia speaking, they want to be flying off at a tangent. The ride itself is providing a force saying that no, it's forcing them. Good pun. It's forcing them into going into the circular motion. Like it wants to fly off, but the ride pushes opposite and keeps it in place. When objects are not rigidly attached to a rotation axis, an outside force must basically push or pull on the object to keep it spinning. Gravity is a great example. You have satellites going around Earth. The force of gravity between satellite and the Earth is that centripetal force to counter the inertia. Why planets orbit around the sun? There's a massive force of gravity between the sun and the planets, and the planets have some initial speed, so the planets want to go off tangentially, but the force of gravity is keeping the planets in line. Another example that isn't gravity would be friction, and this is how cars turn. Or well, cars are a little more complicated, but basically that's uh, by turning the wheel, it's the friction between the wheels and the ground that forces the centripetal force towards the center of the corner that keeps the car turning. You also have like the wheels rotating a bit then too, but um, um, it all goes together. Again, you have like the simplified physics book math of it, and then you have the real world physics of being very complicated and messy. Here's a good one too. The somebody holding onto a toy and spinning it around. The axis symmetry is between the string and the hand. And as you spin that around, the force that you're pulling in towards it, the pull that you pull in towards it, is basically fighting inertia to make it go into the circle. Satellites being a really great example. Gravity between the Earth and Moon is just enough to counteract the velocity of the Moon trying to spin off into space on a tangential trajectory. And again, there's another case that as soon as you start going into like how the tides are affected by the Moon, you get tidal bulges that basically the Moon's pulling the water upwards closer towards it. And it actually does slow down the Earth's rotation a bit. It gets very tricky with how fast you launch things if you want them in orbit. Depending on how far away from the center of the Earth that you want to place your satellite, depends on how fast it needs to go. If you go fast enough, basically it overcomes gravity and you can go off. You can actually go off on a tangent. You can reach escape speed. But you have like bound orbits that, depending on your speed, you have different basically altitudes and different different angular velocities in that. The angular speed, I mean. Something like the geosynchronous satellites, geosynchronous ones, you put them in the correct speed and orbit height that they go around the Earth, that their orbit takes 24 hours. So basically, they stay above the same point on Earth. They're still going around the Earth in a circle, but the Earth is spinning underneath them at the same angular speed. So it takes 24 hours to for the Earth to rotate around, and these geosynchronous satellites also have that 24-hour period. If the tangential speed of the object is not high enough to counteract the Earth's pull, the satellite will start having a decaying orbit. So jumping ahead here, torque is a quantity that measures the ability of a force to rotate an object around some axis. And usually we kind of see it as like a lever arm, that you have a perpendicular distance from the axis of rotation, and then you have the force acting on it. So a lot of times like wrenches are a great example of using torque. In fact, they do have torque wrenches. Torque wrenches are useful tools because they actually limit how much force you can apply on your bolt. And as you can see here, it's related to force. It's your radius times your force. that gives you your torque. This also gives you a preview of momentum as well. Momentum is your momentum, linear momentum, times the radius. You can also figure out how much force you need for how much torque you need. So force is equal to torque over the distance, over your radius. So torque is the force times the lever arm times the angle of rotation. So most of the time you want it to be basically 90 degrees. You want your force to be tangential. That way all your force goes into producing a torque on your object. So a good example of this is trying to open a door by pushing or pulling at the handle versus trying to open the door by pulling or pushing by the hinge. It's going to be much harder to open the door if you're pushing close to the hinge. And much easier to open or close if you have the handle. Because you're further away from that hinge. Basically, like if we go back to here, to get something spinning, you need so much torque. So to get more torque, you can either increase the force or you can increase the distance away from the pivot point. And basically, torque is rotational work. More torque is produced with a longer lever. More torque is produced with more force. So when you're doing work, you want to maximize torque by making the lever arm as long as possible, making rotation easier. So this is the difference between like a long wrench or a short wrench. Why if something like if you're trying to take the lug nuts off your car's tires or wheels, why I can help to get like a pipe or something to put on the lug wrench to give you more leverage, to give you more torque. So moving rotational stuff, dynamics. Torque is your tangential force times the radius. You can simplify that a little bit and say that, hey, this is your tangential force is equal to your mass times your tangential acceleration, which is that second one here. And tangential acceleration is equal to your radius times your angular acceleration. So if we fill that in, we now have m and r squared, our radius squared, times the alpha. And that mr squared basically simplifies down to as the moment of inertia of a particle away from a pivot point. So our tangent or our torque equation can become I times alpha, and this is basically Newton's second law for rotation. So instead of F is equal to ma, we have torque is equal to I alpha. Moment of inertia measures how much of an object wants to keep rotating or to not start rotating. And it really uses calculus with the geometry of the object. And there's a ton of different moments of inertia out there. Basically, every shape is going to have its own calculation of it and how you're spinning things. So a hoop is going to be different than a sphere. And sheets are different from particles, then rods are different from cylinders. So depending on what you're rotating and your axis of rotation, the moment of inertia will change. Some things like to rotate easier than other things. If you actually want to figure out work for rotation, that's basically your torque times how many your angular displacement. So how much of that circle did you rotate the thing? That will give you the work. You also have rotational kinetic energy. That one is, instead of 1/2 mv squared, it's 1/2 I for moment of inertia times the angular speed squared. Oops. And when we were doing conservation of mechanical energy, we had our classic before is equal to our after. Potential energy plus kinetic energy has to equal potential energy plus kinetic energy. Except now, kinetic energy can include both translational, the linear, and the rotational. So if you wanted to figure out how much work and energy and power go into like spinning one of the playground spinners, work is your torque. So how hard you're pushing, how far away from the axis you are, times how much you actually push on it, how much of the angle of the circle you push on it. Kinetic energy, you can figure out by looking at your speed. And power is that torque times your angular speed, angular velocity. Here you basically can go into a whole like unit on simple machines and how they work. They're based on basically mechanical advantage, and lots of it is basically rotational motion to help us do work. So energy is conserved. So the biggest thing of all with simple machines is that the amount of energy is going to be the same with or without the machine. It's all about the mechanical advantage of your force output over your force input. So the idea is that you want to put in a little bit of force and get out a big force. So the bigger mechanical advantage, like if you have a mechanical advantage of 10, if you put in 10 newtons of a push, you get out 100 newtons of push. And that's the whole idea of levers. You put in a little bit of force here, and you get a lot more force out here. That you pivot here at the end. So force going into here, and from our pivot point pushes force out over here. Wheels and axles are basically just different manipulations of torque. Inclined planes like ramps. Basically, you if you have a really long ramp, you can use a little bit of force to push something up the ramp, but you're pushing it for a longer distance than if you just lifted it straight up. Screws are an inclined plane wrapped around a shaft. So basically, this is combining basically kind of like the wheel with the inclined plane. And like if you use like a wedge, that's actually just two inclined planes. Pulleys change the direction of force, and if you use them in a combination, you can actually decrease the force needed, but you're going to pull longer on it. So, like for the example on this pulley system, it has mechanical advantage of 2. So if this is 100 pounds, you can use 50 pounds of force to pull it up. But if you need to lift it up 10 feet, you're going to pull 20 feet of rope. And of course, being physics, if you're actually doing the math, we convert all that into metric system. But we're not doing math today. Here's one that if you're pulling up a cart on a ramp, you want to increase the height of this cart by 1 meter. Your ramp can be 10 meters long, so it ends up being a mechanical advantage of 10. So instead of lifting up like 500 newtons of force to lift up 1 meter, you're pulling only 50 newtons. So that's 1/10 of the force needed, but you're timesing it, your distance covered by 10. So 10 times 50 is 500 Newton meters. That's how much work you did. If you just picked it up 1 meter times 500 newtons for the weight, 500 Newton meters. So both situations are 500 Newton meters. You do the same work. You have the same energy. It's just a matter of how you get there. Anybody going into the medical field, you end up having to take some anatomy classes that might have some physics in them then too. Looking at like lever arms in our hands and that. I do some tutoring off hours for college students and that. And I get quite a few from the medical field that need some help with the torque problems here with like arms and legs and things like that. Basically for this, you have to look at all of your different forces acting on it, and you have the lever, the pivot point here at the elbow, but your muscles aren't right at the elbow. They're connected with ligaments further down on the arm. So you have the force pulling up, you have the weight of the arm here, the center of mass weight. You have, wow, that's a heavy physics book. 8-pound physics book in your hand. Basically, how much does your muscle need to pull up to support the weight of the book? I keep talking about center of mass. But basically the center of mass is if you take all of the mass of an object and you figure out where could you balance it on your finger. So like hopefully you probably have done this before, but if you like take your pencil, because of the different density at the end of it, maybe you have like a really pointy end and maybe a heavy eraser on it. It might not always be like the exact center of the pencil. You might have to move it about a little bit to find that sweet spot. And that's actually what's happening here with these bricks. They kept stacking them up so that the center of mass is still over the desk. So even though this brick is way out over here, the center mass of everything is still supported by the desk itself. And he looks so happy. So if you have like a real blobby shape, or if your object doesn't have constant density, the math can get a little bit complicated. But basically, you're looking for the point that you could balance it on a fingertip. And last but not least, we have angular momentum. Linear momentum is mass times velocity. So our analog here for angular momentum is L instead of P. And that is, instead of mass, we have the moment of inertia. And instead of a linear velocity, we have angular velocity. So when you rotate something and exert a torque on it, The more torque you do, the faster the change in angular momentum. So if you look at here, the net force, not force, your net torque is your change in momentum over change in time. Very much like force could be calculated by your change in momentum over time. Linear momentum of a system will be conserved if your net force is 0. Or angular momentum of the system is conserved if your net torque is equal to 0. So momentum before is equal to momentum after. And if you're doing a collision in that, kinetic energy still is conserved in elastic collision. Momentum is a vector, so we need a direction to it. For that, we use the right-hand rule. You hold out with your thumb out along the axis, and you curl your fingers in the direction of motion. You might have to turn it upside down. So if we're going in counterclockwise, the fingers go counterclockwise, the thumb points up. Our angular velocity is pointing up. Our angular momentum is also pointing up. And this is why counterclockwise is positive, because we think of upwards as positive. So if you're going clockwise, your right hand would have to flip upside down, so you're giving the thumbs down. So that is why it is negative. And this is actually a pretty cool example. I don't have the things, otherwise I would record myself. I might have to buy the stuff eventually. But if you start spinning a bicycle faster and faster and faster and hold on to it, and they actually have a special jig to let you hold on to it with like the handles and that. The wheel is spinning and spinning and spinning. But if you flip it over, angular momentum wants to be conserved, and all of a sudden you're making it so that you have positive L up, and now this wheel is now positive or negative L down. So what's neat about this is if you're standing on a rotational platform that can rotate, to conserve angular momentum, underneath you will actually start to rotate. And as the notes, I guess you can't see that. So if the wheel is upside down, that negative L needs to be canceled out. But you also need the original L to show up. So the angular momentum of this spinning platform will end up being 2L. That way it cancels out. So you'll actually start spinning in the original direction if you flip the wheel around. Angular momentum is also how like ice skaters go from spinning slow to fast to slow. If you watch them, if they extend their arms out, they slow down the spin because the moment of inertia. If we go back to moment of inertia here, moment of inertia is basically your mass times your radius squared. So if you increase your radius by putting your hands out, you're putting more mass away from your axis of rotation. Your moment of inertia gets bigger. Which, if your torque is the same, your alright, not the torque. Let's go back to here. There we go. So if you increase your moment of inertia, we know the momentum stays constant, so your omega will get smaller. So that's why ice skaters will slow down when they extend their arms outwards. And if they pull their arms in towards their chest, your moment of inertia gets smaller, so your angular velocity would increase. to keep that L the same. And that's basically um, most of rotational physics in a nutshell. Of course, if you go more in depth with things, you get a lot more complicated. But that's pretty much it. So hopefully you found this informational, and um, was a good supplement for what else we had done this year. So thank you for listening, and I hope you have a great day wherever you are.